Hi dears, today we can see some results on convergent sequence, subsequence and cauchy sequence. So the first result, let P and be a sequence in a metric space. Then first option, first result, Pn converges to a point P if and only if every neighborhood of P contains all but finitely many of the terms of Pn. So for that we can see an example sequence 1 by n belongs to n. So here you can see 1 and 2, that is 1 by 2 and 1 by 3, 1 by 4, etc. etc. It converges to point 0. So here we can see this is converges to the point P is what? Here 0. If we take the neighborhood of 0, we can see finitely many terms of Pn, because here you can see infinite number of terms. But when we approaches to the limit point, the small neighborhood contain all but finitely many terms. ഇവിടെയൊക്കെ നോക്കിയെങ്കിൽ infinite number of terms ഉണ്ട് 3, 4, 5, 1 by 100, 1 by 1000, 1 by etc. etc. But when you approaches to the limit point 0, അതിന്റെ neighborhood എടുക്കുമ്പോഴത്തേക്ക് it contains of finitely many terms of Pn. So second one, if P belongs to P and P dash belongs to P and the sequence Pn converges to P and P dash, okay, the sequence converges to the limit point P and P dash, then you can say that P and P dash are equal because limit is unique. Now third one, if sequence Pn converges, then sequence Pn is bounded. That is, every convergent sequence is a bounded sequence in a metric space. Then D, if P is a limit point of E and a sequence Pn such that P is equal to limit n tends to infinity Pn. This is the limit definition. If Pn is a sequence and P is a limit point, then it can be written as P is equal to limit n tends to infinity Pn. The second result, if Pn converges to point P, if and only if every subsequence of sequence Pn converges to P. That is, sequence Pn converges to P means the subsequence of the sequence Pn is also converges to P. For example, sequence 1 by n converges to 0. The subsequence is 1 by 2n, right? 1 by 2n is the subsequence of 1 by n. That is also converges to 0. Now third result, if sequence Pn is a sequence in a compact metric space, then the subsequence is converges to the point in X. So here we can say that sequence Pn is a sequence in the compact metric space. And we can say that the subsequence is converges to the point. That point belongs to the compact metric space. Now the fourth result, every bounded sequence contains a convergent subsequence. So just before we see that in a usual metric space, every convergent sequence is a bounded sequence, but the converse is not true. But every bounded sequence contains a convergent subsequence, but this is possible for Rk, that is Euclidean space. So every convergent sequence is a bounded sequence. Every convergent sequence is a bounded sequence. Converse not true, but bounded implies convergent subsequence, but this is possible for the Euclidean plane Rk. Now we can see diameter. So E be the subset of metric space, S be the set of all real numbers, D of P comma Q, then supremum of S is called the diameter of E. So this is nothing but diameter E is the supremum of the distance between the 2 points. Supremum of the distance between the 2 points, or you can say that LUB of the distance between the 2 points P comma Q. Similarly, we can see some examples of the diameter. The diameter of the empty set is equal to minus infinity. So if A is a non-empty subset, then we can say that diameter A is bounded if and only if A is a finite set. Okay, so A is finite if and only if diameter of A is bounded or the converse one. Then diameter of A is equal to 1. This is possible if A is a discrete metric. Discrete metric means the diameter of A is equal to 1. Then you can see one more. In R, the diameter of an interval is equal to the length of the interval. So for example, the diameter of the interval here 0, 1, that is the diameter of the interval. So it is equal to 1 minus 0, that is equal to 1. The same way we can find the diameter. So diameter is equal to, in R, that is the length of the interval, or in the set we can say that LUB, or the supremum of the distance between 2 points. And this is the one. If Pn is a Cauchy sequence, if and only the limit of the diameter is equal to 0. If it is Cauchy sequence, then the limit diameter of Pn is equal to 0. Seventh one, E bar is the closure of the set. So before itself we seen E bar is equal to E union E dash. That is the set union, set of all limit points. So that is closure. If it's so, diameter of E bar and diameter of E are equal. Then eighth one, if Kn is a sequence of compact sets, Kn is a compact set, and the second condition Kn contains Kn plus 1, then the third condition, a limit n tends to infinity, diameter of Kn equal to 0, then you can say that intersection n equal to 1 to infinity Kn contains exactly 1 point. If these three conditions satisfied, compact, Kn contains Kn plus 1, limit diameter Kn equal to 0. If it's an intersection 1 to infinity, Kn contains exactly 1 point, as like contour intersection theorem. Then the ninth one, in a metric space, every convergent sequence is a Cauchy sequence. Every convergent sequence is a Cauchy sequence in a usual metric space. Then 10th one, if sequence Pn is a Cauchy sequence in X and that X is a compact metric space, then we can say that the sequence Pn converges to the point, that point belongs to the compact metric space. Right? Then we can see the next result. In Rk, every Cauchy sequence converges. So just before we see that every convergent sequence is a Cauchy sequence. This is for the usual metric space, and here every Cauchy sequence is a convergent sequence. This is possible for the Euclidean space Rk. Then 12th one, a metric space in which every Cauchy sequence converges is said to be complete. So complete metric space means the condition is here, every Cauchy sequence converges. Every Cauchy sequence converges implies complete metric space. The examples of complete metric space are all compact metric space are complete, all Euclidean space are complete, and one more is here, a space of all rational numbers is not complete. Then the 15th result, closed subset of a complete metric space is complete. Then 17th one, if sequence Sn is monotonic, either monotonic increasing or monotonic decreasing. If it's so, sequence Sn converges if and only if sequence Sn is bounded, that is convergent implies bounded. Then 18th one, if p greater than 0, limit n tends to infinity 1 divided by n for p equal to 0. For example, limit n tends to infinity 1 divided by n for 3 by 2, which is equal to 0, since p equal to 3 by 2 is greater than 0. Similarly, the 19th one, if p greater than 0, limit n tends to infinity, nth root of p is equal to 1. The same way 20th, limit n tends to infinity, nth root of n equal to 1. And 21, if p greater than 0 alpha is real, then n power alpha divided by 1 plus p the whole power n is equal to 0. The 22nd, if modulus x less than 1, then limit n tends to infinity, x power n is equal to 0. So this 18 to 22nd, while we're doing the problems, we can apply this. Thank you.